Now let's talk about linked lists. So linked lists, it's named kind of like links in a chain, right? So we've got a head pointer that points to a node that then has some data and points to another node, and eventually points to one that doesn't point any farther. So here in our top diagram, we show head points to the node containing 7, points to the node containing 10, points to the node containing 4, points to the node containing 13, doesn't point anywhere. How this actually works is that a node contains a key, which in this case is these integers, and a next pointer. The diagram below shows more detail of what's going on. So head is a pointer that points to a node, and that node contains two elements, the value 7, and then a pointer that points off to the next node that contains a key 10, and a pointer that points off to the next node 4, points off to the next node 13. 13's next pointer is just nil. What are the operations that can be done on a linked list? Okay, there are several of them. And the names of these sometimes are different in different environments and different libraries, but normally the operations provided are roughly these. So we can add an element to the front of the list, and that we're calling push front. So it takes a key, adds it to the front of the list. We can return the front element of the list. We're calling that top front. Or we can remove the front element of the list, called pop front. These same things that we can do at the front of the list, we can also do at the end of the list. With push back, later on in a later module we'll actually use the word append for that, or top back, or pop back. These seem uniform in there, but there is a difference in that the runtimes are going to be different between those, and we're going to talk about that. You can find whether an element is in the list, and that's as simple as just running yourself down the list looking to find a matching key. You can erase an element, and then again, run yourself down the list till you find a matching key, and then remove that element. So these latter ones are both order n time. Is the list empty or not? That's as simple as checking, is the head equal to nil? We can add a particular key. If we want to splice in a key into a list, we can actually add in a key either before a given node or after a given node. So let's look at the times for some common operations. We've got here our list with 4 elements in it, 7, 10, 4, and 13. Now we go ahead and push an element to the front. So we push 26 to the front of the list. So the first thing we do, create a node that contains the 26 as its key. And then we update our next pointer of that node to point to the head, okay, which is the 7 element. And then update the head pointer to point to our new node. And that's it, we're done. So it's order 1. Allocate, update one pointer, update another pointer, constant time. If we want to pop the front element, it's clearly finding the front element is very cheap here, right? We can just look at the first element and return it. So top front is order 1. Pop front is also, turns out, going to be order 1. First thing we're going to do, update the head pointer. Then remove the node. That's order 1 operation. If we want to push in the back, okay, and we don't have a tail pointer, we're going to talk about a tail pointer in a moment, then it's going to be a fairly expensive operation. We're going to have to start at the head and walk our way down the list until we get to the end and add a node there. So that's going to be order n time. Similarly, if we want to top back or pop back, we're going to also have to start at the head, walk our way down into the last element. Those are all going to be order n time. If we had a tail pointer, some of these have become simpler. Okay, so we're going to have both a head pointer that points to the head element and a tail pointer that points to the tail element. So that way getting the first element is cheap, getting the last element is cheap. Let's look at what happens when we try and insert when we have a tail. We allocate a node, put in our new key, and we then update the next pointer of the current tail to point to this new tail, and then update the tail pointer itself. Order 1 operation. Retrieving the last element, so a top back, is also an order 1 operation. We just go to the tail, find the element, return the key. If we want to pop the back, however, that's a little bit of an expensive operation. Okay? We are going to need to update the tail to point from 8 to 13. So we're at 8 right now, we want to go to 13. The problem is, how do we get to 13? Okay? We don't have a pointer from 8 to 13. We have a pointer from 13 to 8. And that pointer doesn't help us going back. So what we've got to do is, again, start at the head, walk our way down until we find the 13 node that then points to the current tail. And then update our tail pointer to point to that. And then update that next pointer to be nil. So that's going to be, and then we can remove that old node. So that's going to be an order in operation, because we've got to walk all the way down there. Okay? Because even though we have the tail pointer, we don't have the next to the tail pointer. We don't have the next to last element. The head is different. Because our pointers point this way, if we have the head, it's also cheap to get the second element, right? And one more to get the third element. But the tail pointer doesn't help us get to the next to the last element. Let's look at some of the code for this. So for push front, we have a singly linked list. We're going to allocate a new node, set its key, set its next to point to the old head, and then we'll update the current head pointer. If the tail is equal to nil, that meant that before the insertion, the head and the tail were nil. It was an empty list. So we've got to update the tail to now points to the same thing the head points to. Popping the front? Well, if we're asked to pop the front on an empty list, that's an error. So that's the first check we do here. And then we just update the head to point now to the head's next. And just in case that there was only one element in the list and now there are no elements, we check if our new head is nil, and if so, update our tail to also be nil. Pushing in the back, allocate a new node, set its key, set its next pointer, and then check the current tail. But if the current tail is nil, again, it's an empty list. Update the head and the tail to point to that new node. Otherwise, update the old tails next to point to our new node, and then update the tail to point to that new node. Popping the back, more difficult, right? If it's an empty list and we're trying to pop, that's an error. If the head is equal to the tail, that means we have one element, so we need to just update the head and the tail to nil. Otherwise, we've got to start at the head and start working our way down, trying to find the next to last element. When we exit the while loop, P will be the next to last element, and we then update its next pointer to nil and set our tail equal to that element. Adding after a node, fairly simple in a singly linked list. Allocate a new node, set its next pointer to whatever node we're adding after, to its next. So we sort of splice in, and then we need to update the node pointer, the one we're adding after, so that it points now to our new node. Okay? And just in case that node we're adding after was the tail, we've got to now update the tail to that new one. Adding before, we have the same problem we had in terms of pop back, in that we don't have a link back to the previous element. So we have no way of updating its next pointer other than going back to the beginning of the head and moving our way down until we find it. So add before would be an order in operation. So let's summarize what the cost of things are. Push front, order 1. Top front, pop front, all order 1. Pushing the back, order n, unless we have a tail pointer, in which case it's order 1. Top back, order n, again, unless we have a tail pointer, in which case it's order 1. Popping the back, order in operation, with or without a tail. Finding a key is order n. We just walk our way through the list trying to find a particular element. Erasing, also order n. Checking whether it's empty or not is as simple as checking whether the head is nil. Adding before, order n, because finding the previous element takes order n, because we've got to walk away from the head to find it. Add after, constant time.